So we're looking at this slide here in the chapter 2 PowerPoint. And what I was just saying right before I hit record is that, this is not really a class in electronics, right? So I'm not here to teach you guys how to be electrical engineers or electromechanical repair people or anything like that. But some of the stuff that we do with IoT kind of crosses over into that area. And it's really kind of helpful to know some of the basic terms and concepts. And this is on a really basic level. So I'm not going to, for example, challenge you guys to come up with electrical formulas and work them out mathematically. That's not what I do. If you were studying electronics formally, they totally would make you do that, right? So my goal is not to do that. Basically, what is electronics? Well, it's anything that allows electrical current to kind of flow through the system and operate it. And it could be something as simple as a light bulb, or a radio, or something much more complicated like a computer. And all those different systems are powered by electrical energy, whether that energy comes out of the wall, whether it's a battery, or some weird combination of the two. The way that electricity basically works is we have, when we look at a physical atom, there's a part of the atom called the electron. It's the electrons that are basically flowing that create the current, right? And there's kind of a flow that happens. All right, so there's different aspects to electricity, a couple of really basic kind of ideas here. And once again, I'm not going to test you on how to do the math on these. But there's a combination of how circuits are connected. So basically a circuit really is when the wires typically connect to each other, connect to various components, allow the electricity to flow, and then perform some action. We've been able to ramp up this concept, and I want you to think about how fresh electricity is in the terms of human history. When did electricity first get discovered? I mean, in terms of modern times. Does anybody know this one? Yeah, I mean that's the classic example, right? So the cartoon of Benjamin Franklin with a kite, and there's a key at the end, and the lightning strikes the kite, and it travels down and sparks up the key, and he discovered electricity. Well, the lightning's been happening for much longer than that, right? But what he did is he discovered that might be able to be used to do something. More importantly, what they really used it for back then is they realized that sometimes lightning would strike buildings and set them on fire. And if they would put a metal rod up at the top of the building and then run a copper cable into the ground, they could redirect that energy into the ground and not have it destroy the building. And to this day, if you guys go out in wide open spaces where there's barns, people that have tall barns, ideally, they should have a lightning rod or two on top of the crest of the barn, and then they ground it. Whenever you're in your house and you have an electrical system, all the ground ports, like in your plugs, ultimately connect to the ground outside the house somewhere, usually via the plumbing, right? So they ground to the plumbing, and the plumbing goes into the ground. But it's for the same reason. If there's a shock or a short or a lightning blast or whatever, it travels to there instead of destroying things. That's kind of the concept. So those are kind of some of the basics of circuitry. This really important concept of Ohm's law is that any circuit that has voltage going through it with a certain amount of current will also have a certain amount of resistance to the electricity flowing through, right? And that kind of happens naturally. So the longer your run of your circuit, the more resistance you have, typically. And that's just kind of something that naturally occurs. When you start to learn about electricity, often people who create electronics usually start at a drafting board or a diagram showing how electricity flows. Really important concepts here to kind of think about are, we usually have electricity that's got a positive and a negative voltage. So when you pick up a battery, right, there's a positive side and a negative side. Electricity flows out of the positive side and back into the negative side, to complete a circuit. So when you see a circuit like this and see the little plus and minus, what it's showing is the flow of electricity, the current follows the output of the positive. This little thing is indicative of resistance, and it's measured in ohms, based on Ohm's law. And then this is a diode or some sort of a thing. And when we think about diodes, we think of, because now most of our lighting in our buildings, including the ones in this room, are LED, light emitting diodes. So they're basically an electrical component. I have a little LED right here on this breadboard, and I'm sure the online people can't even see it. That is basically one of those. So if the current flows through it correctly, it lights up. So that's kind of how that works. Couple different kinds of circuits. One kind of circuit is what we call a series circuit. So if you look at that one kind of closely, you'll notice that the power flows out of the battery. There's a switch that turns it on and off, but then there's two light bulbs. And those bulbs are one right after the other in the series, right? And if we wire them parallel, we split the electrical current and the electricity flows through both sides at once. Think about this. In a series circuit, if one light bulb dies, the other one doesn't work either because the circuit's broken. In a parallel circuit, one light bulb could go out and the other one could stay on. And if you've ever had any Christmas lights, like the old-fashioned kind, and like one bulb goes out, it's like, man, there's like 500 of them on here. I got to check each one to figure out which one's bad. Hopefully it just broke, like the cat got it or something. But yeah, so two different types of circuit, parallel and series. There's a bunch of different kinds of components that we can hook up. And I don't know if you can make out these graphics here, but I can always make them a little bigger. But I also have one on this little breadboard that I have here, which is a little resistor, this little blue thing. And we're going to need to use that when we toy with some stuff, because you have to have the right amount of voltage going to the bulbs in order for them to work correctly. And if you sometimes send too much current into something, it can blow it up or make it catch fire even. And so often we use resistors on purpose to tame the electricity, to bring it down to the right voltage, create enough resistance so we're not overloading something. Other components too, like this last one here, which we call a capacitor, which basically doesn't resist the energy, but it stores it. And then we have these little diodes and transistors. And what's I think really fascinating about like some of these components, like a transistor is just like a little, basically like a switching device is really kind of the best way to say it. And one singular transistor looks like one of those little diagrams there, but when we build a CPU for a computer's got billions and billions, and that's a multiple, right? Billions times. So there's so many of them, you can't even count them that are on a CPU, and it's like this big, the size of a quarter, basically. How did they do that exactly? I think it's mind-boggling, right? That we've been able to develop the technology from like holding a kite in the air in the early 1800s to a couple hundred years later, we have smartphones and, we're spoiled as heck with all the technology that we have. Very, very fascinating stuff. Another really important concept is when we're working with electronics and we're sending signals through the electronics. So this is a really common usage. Signals can travel either digitally or what we call analog. Analog is a waveform. So a really good example is when I'm speaking with my voice generates sound waves which are inherently analog. There's imperfections in them and all that sort of stuff. But if I was to plot it on an oscilloscope, after picking it up on a microphone, you would see waveforms. They might be a little jagged, but they're basically waveforms. Digital, which is how we listen to most of our media, so all our TV now, our audio pretty much is all digital, is an approximation of the analog waveform. It's not, and so it can never really be as perfect as the analog waveform, ironically, but digital is always cleaner because it can use what I call the horseshoe effect, which is like close works. So you can have a kind of weak signal with digital, but it still transmits completely. Where with analog, if it's kind of a weak signal, you hear the noise, right? And so that's why we really kind of don't use it for like audio anymore. Although there's people that are kind of having a big argument about it. All right. So, interestingly, one of the things that you do with some of these IoT devices and a big usage, especially in industry, is we have these computer controlled mechanisms. How can we use those to control devices? And a lot of it really kind of comes down to you have to sometimes plan things out. And so once again, I'm not here to teach you how to be an electrician of any sort. We're just trying to use some IoT devices and kind of get them to do some cool stuff, hopefully, and then kind of trip your mind to possibilities. But normally what you do is you design something first. Packet tracer is kind of one of those tools that you can potentially use to do that, by the way. Some people still use paper and pencil, but most people are using software tools these days. And then you do something where like you build it like a prototype in like this little breadboard I'm holding in my hand, which is kind of a generic circuit board, allows me to connect power to it and various devices to see in principle if the concept works, right? And then if the concept works, then you can actually burn it onto a real circuit board and make something out of it that does the specific task, right? Lots of things are created that way. Most circuits are really actually pretty simple, and actually the little graphic here is kind of neat because, as you'll notice, this is a breadboard almost identical to the one I have in my hand. And you'll notice what they have on there is a little LED light. It happens to be yellow, just like the one in my hand. And what do they have? They have a 9-volt battery attached to it. It feeds into the board. And I don't know if they're showing it here, but there is another device here called a resistor, right, which is taming the voltage a little bit. And then the light lights up. And this is something that we can easily do here in class. In fact, we'll get to the point where we play with some of this stuff, so just so you get a feel for it. Once again, not trying to make you an electrician, but just to show you. What does happen with a lot of people that get into this IoT stuff, by the way, is they like, wow, I can do that with it. I got this really cool idea, right? And then you end up like concocting like weird stuff, right? Jerry Gifford, which some of you guys might have as an instructor or had as an instructor, he's one of those tinkering kind of guys. Like, he actually borrowed me some of his gear because he has so much of his own. Like, he does these really quirky crafts. Like, one of them, for example, is he takes mannequins and turns them into lamps, right? And then what he does is he puts Arduinos inside of them and then programs them to like light up their eyes and like weird stuff like that, So you have to kind of be a little bit of a geek to go that far with it. But if you were ever a kid that ever like took something apart and tried to figure out how to make it work or fix it or whatever, that might be you, I mean, it's kind of an innate thing. I tinkered a lot with electronics when I was younger, mostly because I played music and my music stuff would fail and I would have to figure out how to solder it or get a power supply or replace a part to make it work again because I was too much of a cheapskate to pay somebody else, right? But given all the information that we have out online right now, you'll notice how cool the things you can do. Building simple circuits is fun, but what's kind of also cool is that you can also, using an Arduino or a Raspberry Pi, write computer code to control those circuits, with an intelligence, right? And there are some tools, and we'll tinker with those. The Arduino IDE is one I hope to play with tonight. And you don't really have to learn how to necessarily be a computer programmer per se to do this stuff, but it doesn't hurt, right? So like I know how to code, so I kind of have like a little bit of a leg up. But a lot of these examples are pretty simplistic, and when it's as simple as just turning a circuit on and off, the code is actually pretty simple in many regards. This is an example of what the Arduino IDE looks like. We'll take a look at that in a little while, so I'm kind of going to jump over that a little bit. There are different kinds of devices that we can hook up to these IoT systems. So we can actually hook up different types of sensors. So they can be things that, temperature or motion or whatever, right? Sound, you can have those kind of sensors. then those sensors can then be used to trigger a circuit on and off, and that might be to turn on a motor or a light switch or whatever you can electronically control. I think that's kind of fun. They do have the packet tracer that we are going to be doing, and we're not doing it this week, by the way, we're doing it next week in class, is to actually do this little setup here where we will create what they call an end-to-end IoT system model. And that is where we actually can connect things up and inside a packet tracer make things happen, right? Some of the reasons why we do the virtual labs is because when we get to like actually messing with equipment, I do have equipment in the cabinets. There's kind of like this whole process of pulling it out and setting it up and packing it up and putting it all away. So we have to be kind of selective about which ones we do. And sometimes it's helpful to kind of do the virtual labs first before you do the physical ones. And you'll see why, right? But physical is always funner because you actually get to touch it and see it, and you get a better sense of satisfaction in my mind, right? All right, so that's kind of my chapter 2 PowerPoint. So I'm gonna stop the recording here.